Our last example for sediment transport will be the estimation of, again, the total amount of sediment which is being moved. We're going to use Yang's method because it allows for the calculation of several other parameters. If you'll notice in the previous example, we were given the volumetric sediment transport rate per unit width. Oftentimes that information is not available. So to use Yang's method, we're going to need several equations. Equation 10.8 is the dimensionless sediment particle diameter. Then we need the shear velocity equation and the shear Reynolds number. Once we get the shear Reynolds number, we would be able to use the modified Shields diagram. We also need the particle fall velocity, and as I mentioned in the previous video, the particle fall velocity is necessary so we know if the particles can actually settle out or continue to be suspended in the flow. So the particle fall velocity to W sub f can be computed using either equation 1010 or equation 1051 and 1052. We need the dimensionless critical shear stress from a Shields diagram. Once again, the definition of some of the parameters. The d star is the dimensionless sediment particle diameter. Gamma sub s, the specific weight of the sediment. Gamma, the specific weight of the water. D, the diameter of the sediment. Nu, kinematic viscosity of the water. U star is the sediment particle shear velocity. R sub E star is the shear Reynolds number. W sub F, sediment particle fall velocity. R sub H, hydraulic radius. S sub F, friction slope, which for these examples we're assuming it's equal to the bottom slope. D50 is the sediment particle diameter, where 50% of the sediment particles are smaller by weight. And F star is the factor for calculation of the sediment particle fall velocity. The critical shear velocity can be determined by rearranging the dimensionless critical shear stress equation. Then Yang provides a criterion to tell if the bed load dominates or if the suspended load dominates, using the shear velocity divided by the fall velocity. The average critical channel velocity can be computed either using one equation, but you have to evaluate the range of that equation. So you can see there are two alternatives here. If U star times D50 divided by nu, which would be the shear Reynolds number, is greater than or equal to 70, then you get the critical channel velocity from this ratio. If the shear Reynolds number is less than 70, then you get the critical velocity using this equation. The total sediment concentration comes from equation 1075. And you can see there are 6 parameters in here: A, B, C, D, E, and F. Those are not numerical here because there is a set of those for both sand and gravel. So the constants for Yang's equation, if you are dealing with a sand, which according to the American Geophysical Union is between 0.0625 to 2 millimeters, you would use these coefficients right here. If you have gravel sediment, which go from 2 to 64 millimeters, you would use this set of constants. The source of this is from Sturm, 2010, the Open Channel Hydraulics textbook, table 10.1. In the HEC-RAS reference manual, they have a computation of Yang's method, and they use this example. So they have the velocity of the channel is 5.46 feet per second. Q is equal to 5,000 CFS. The hydraulic radius is 10.68. The D50, 0.0023 feet, and the friction slope is 1/10,000th. The specific gravity, 2.65. Specific weight of water at that particular temperature, not quite 62.4. They use gravity of 32.2 and the value for the kinematic viscosity of 1.315 times 10 to the negative 6th feet squared per second. So from this information, they go through and they calculate the total sediment concentration using Yang's method. Now, I have also developed a lingo file that does the same thing. Here are the answers from the HEC-RAS reference manual. You have been provided a lingo file student version where when you complete it, you should be able to come up with the same answers that were found in the HEC-RAS reference manual.